In this lesson, we'll learn about lifetime elision. The word elision means the act of omitting something, leaving something out. So lifetime elision means omitting or not writing out lifetime annotations in situations where the borrow checker can infer the lifetimes automatically. So previously, when we first wrote the select first two elements function out, we did not provide these generic lifetime annotations, and the code still compiled. And that is due to the lifetime elision rules behind the scenes. And we're going to talk about what they are throughout this section and a future one. There are 3 lifetime elision rules that the compiler will follow, and it is possible that future versions of Rust will support additional ones as well. So the borrow checker is going to use these 3 rules, and it's going to try to figure out the relationships between the lifetimes of references. And if it's able to do so, then we do not need to provide any lifetime annotations. And if the borrow checker cannot conclusively figure out the relationships, then it's going to fail to compile and will require the developer to provide them manually. So the first elision rule is this: the compiler assigns a lifetime to each parameter that is a reference. Not to every parameter, but to every parameter that is a reference. And I actually want to show you this behind the scenes. So what I'm going to do is enable a specific setting from the Rust Analyzer VS Code extension that's going to show us the automatic inferred lifetimes that the compiler is thinking about. So you do not have to follow along, because this setting that I'm going to change will only last for the duration of this lesson. But I'm going to go into my VS Code settings, and here I'm going to go into my workspace, and I'm going to search for elision hints, and I'm going to find a setting here from the Rust Analyzer extension, and this elision hints setting is set to never, which means never show type hints for lifetimes. Never show the inferred lifetimes that the borrow checker is thinking about. I'm going to swap this setting to always, so we're always going to see them, and then we're going to see some interesting results when we write out our future functions. So let me show you an example. Above this one, I'll declare a basic function called myAwesomeFunction, and I'll begin by giving it a value parameter, and I'm going to set that to be a reference. It doesn't matter what it is a reference to. This rule will apply to any kind of reference parameter. So arbitrarily, let's pick a reference to an I32. So you'll notice here is that special pop-up that we're now seeing from the extension. So this is an inferred lifetime, and the borrow checker is just going to start labeling the lifetime annotations numerically. But remember, the name is arbitrary. So tick 0 is no different than tick A. It's just an arbitrary lifetime name that the borrow checker is thinking about, and it's going to assume that that lifetime is the lifetime of the value parameter. But remember, every single reference parameter is going to get a single independent lifetime. So for example, if I declare a second parameter that is also going to be a reference, let's say string slice, well, now we're going to see this syntax right here, very similar to declaring 2 generic types, but this is 2 generic lifetimes called tick 0 and tick 1. The borrow checker is simply proceeding in sequential numeric order and naming them. It's going to assume that the value reference parameter is related to generic lifetime tick 0, and the second reference parameter is related to generic lifetime tick 1. So the compiler is just assigning these sequential lifetimes to every reference parameter. Parameters that are not references are not going to get any of this. So for example, if I just declare a third parameter of type string, we're not going to see that inference appear in VS Code, and thus the borrow checker is similarly not inferring anything here. Remember, the whole purpose here is to prevent dangling references. So where the borrow checker is really concerned is when we're dealing with parameters that are references, because those are going to be the only thing that we could return as a reference out of the function if we have a reference return value, and that is where the capacity for dangling references starts to become possible. So that's why the borrow checker is only concerned about the references and tracking their lifetimes, right? Own values don't really have to deal with the same concern of lifetimes, because with the scenario of the third parameter, we're either going to return it to preserve it, or we're going to let it be deallocated and the memory will be cleaned up. So there's no chance of a dangling reference. All right. The second lifetime elision rule is this. If there is one reference parameter and the return value is a reference, the borrow checker will infer that the parameter's lifetime will also apply to the return value's lifetime. So it's going to make the association that the lifetimes of the reference parameter and the return value are related. Basically, this is the exact same idea that we were talking about over the course of the previous lessons and why this code compiled before we annotated it. But just to show you that right here, let me go back to just having a value parameter. And let me declare the type here of the return value to be a reference to an I-32. The code right now will not compile because our function body is not living up to the promised lifetime contract, right? We have declared that we are going to have a return value that must also have a lifetime connected to the lifetime of the value parameter. And we're not doing anything in the body of the function, so we're not living up to that promise. So if I declare the simplest function body I can, which is just returning the value parameter, the code will compile. But more importantly, take a look at this inference here. This is the second rule in action. If we have one reference parameter, and we do, and the return value is a reference, Rust will infer that their lifetimes are related or associated. So again, the borrow checker's concern here is with parameters that are references. So if I declare a second parameter set to a string, you can see that the second elision rule is still going to apply. Rust is going to say, I have one reference parameter and a reference return value. I'm going to assume that they're related and that their lifetimes are connected to one another in some way. The return value is a lifetime that must be contained within the reference lifetime that value is coming from. Very similar to the idea that we talked about in the previous lesson. It's just being assumed or inferred behind the scenes because there's only one reference parameter to deal with. So it's the type of the parameter, right? And how many of them there are. So if I reverse the order of these parameters, the same rules are going to apply. Notice here we have one reference parameter. It's now in the second position, and Rust will assign every reference parameter a generic lifetime annotation. That is the first rule. And then the second rule is if there is a return value that is a reference, Rust will associate or infer the lifetime of the reference parameter to the lifetime of the returned value. So the order doesn't matter, it is the type. So it's with these two rules that we can now understand why the code from the previous lessons compiled without explicit lifetime annotations. So if I get rid of our manual declarations right here, you're going to see that the lifetime rules are going to reach the exact same conclusion that we explicitly manually annotated. Rust said, for every reference parameter, I'm going to give it a generic lifetime. There's only one, so I'll create one generic lifetime called tick0 and assign it to items. That is its associated lifetime. And then since there is a return value that is a reference, Rust will assume that these two lifetimes are related, and thus the compiler and the borrow checker understand that this return value must live within the lifetime of the referent that items is coming from. All right. So kind of obvious to infer this because it's the only logical way it could work, right? A return value cannot be a reference to an owned value, whether it be an original piece of data or a parameter. So it has to be coming from another reference. And if there's only one reference in the parameter list, then the two must be related, right? That is an obvious thing because it is the only possibility, right? It is the only technical way that could work. Where we're going to run into issues and where the elision rules are going to not be enough for the borrow checker to compile is when we start dealing with multiple reference parameters. So for example, if I declare a second parameter, let's say right here, I change second to be a reference to a string. Now we have the potential for two lifetimes, which means two different regions of code for which the second parameter and the value parameter will be confined to, because those references must live within the lifetimes of their reference, which could be two different lifetimes or two different regions of code. And now the borrow checker is not going to be sure what promise we are going to be making with the return value. Is it something that has to live within the value reference lifetime or something that has to live within the second reference lifetime? There's the possibility that these two could be different, and yet we're returning a reference. So Rust does not know what it needs to guarantee, which referent we need to promise that the function body is going to dictate that the return value be connected to. We're going to talk more about multiple function parameters that are references in the following lessons, and I will see you there.